We physicists have waited 100 years since 1916 for this photograph.
Astronomers said they captured a picture of the supermassive black hole at the center of the Milky Way galaxy.
Black holes rank among the most mesmerizing phenomena in the vast expanse of the universe. These colossal titans wield an unfathomable might, commanding immense power that boggles the mind. Yet paradoxically, they shroud themselves in an impenetrable cloak of invisibility, keeping their secrets hidden from our curious gaze. However, fueled by tireless dedication and relentless exploration, we have embarked on a transformative journey of discovery. In the blink of an eye, we have transitioned from utter ignorance about black holes to gradually unraveling the enigma. And just when you thought the realm of black holes couldn't become more bewildering, prepare for a revelation of mind-bending proportions. Michio Kaku, a luminary in the field, has just shattered the boundaries of knowledge by offering us an unprecedented glimpse into the mysterious depths within a black hole. So join us as we voyage into the unknown and unlock the mysteries that dwell within these cosmic behemoths. Black holes are both captivating and fearsome, as their gravitational force prevents anything, including light, from escaping. Objects nearing a black hole are inexorably drawn in, never to be seen again. Albert Einstein's theory of general relativity, published in 1916, predicted their existence, but it took 50 years to find evidence. The discovery occurred in the 1960s while studying the Cygnus constellation, where an X-ray emitting blue star revealed its orbit around a black hole, confirming their existence. This breakthrough not only validated Einstein's theory, but also emphasized the need for further exploration. This black hole, named Cygnus X1, located 6,000 light-years away in the Cygnus constellation, is remarkably bright and dense, with an intense gravitational pull that even traps light, hence the term black hole. After discovering Cygnus X1, scientists embarked on a quest to find other black holes. The Milky Way alone may house over 100 million black holes, but their elusive nature makes it challenging to determine an exact count. And in 2021, scientists achieved a significant milestone by capturing the first clear photograph of a black hole, specifically the M87 black hole. They took multiple photographs over consecutive nights and stitched them together to fill gaps and gather evidence. This revealed that black holes consist of 3 layers, challenging the notion of a single void. Reaching the nothingness inside a black hole requires traversing the first 2 layers. The first layer, known as the event horizon, marks the point of no return. Once crossed, there's no escape, and you will be pulled into the black hole. The second layer is the photon sphere, where light orbits the black hole. Any light entering the region becomes trapped by the immense gravitational pull. Finally, the third layer is the singularity, where matter entering the black hole is compressed into an infinitely small point. At the singularity, the laws of physics break down, defying prediction. Adding to the complexity, each black hole is unique despite following the 3-layer concept. Their functionality can vary significantly. Unlike other objects, studying black holes directly is impossible. Scientists must rely on indirect observations of the radiation emitted and the surrounding gas and dust. And sending a probe like Voyager into a black hole is unfeasible, since anything crossing the event horizon is drawn toward the singularity, ultimately crushed into nothingness. Investing billions of dollars in such endeavors would yield no valuable insights due to the destructive nature of black holes. However, researchers have been actively engaged in various theories and explanations surrounding black holes, each contributing to the growing intrigue. To gain a profound understanding of black holes, NASA scientists focused on the core of the M87 galaxy. They observed an immensely powerful whirlpool of superhot hydrogen gas spinning at an astonishing speed of 1.2 million miles per hour. Surprisingly, instead of violently dispersing, the spinning gas remained intact. This led scientists to infer the presence of an enormous mass concentrated at the galaxy's center, which could only be a black hole. This colossal object weighed 2 to 3 billion times more than the Sun. Yet the spinning nature of black holes is not limited to this theory alone. In 1963, New Zealand mathematician Roy Kerr utilised Einstein's equations of gravity to provide the best description of a spinning black hole. Kerr proposed that a spinning black hole would not collapse into a point, but rather form a ring of fire or a thin disk. This spinning disk, known as the ergosphere, resists collapse due to centrifugal forces. Within the ergosphere, the laws of physics begin to break down. Kerr's solution also intriguingly predicted the existence of an Einstein-Rosen bridge, commonly referred to as a wormhole. This theoretical passage through space-time connects separate regions of the universe or even parallel universes. According to this concept, instead of being annihilated, an individual falling into a black hole would traverse a tunnel through the ring of fire and emerge from a white hole in a parallel universe. To grasp these phenomena, a new theory is essential, merging gravity and quantum radiation, a sought-after theory of everything. Michio Kaku, a renowned physicist, has long pursued such a theory. Superstring theory stands as the sole promising candidate, uniting gravity and radiation. It posits that subatomic particles are vibrating strings, forming a symphony within the universe. Like musical notes on a violin string, distinct vibrations correspond to different particles. Superstring theory possesses a captivating aspect. The movement of a string through time warps the very fabric of space, conjuring enigmatic phenomena like black holes and wormholes, a tapestry woven by Einstein's equations. Astonishingly, this theory not only unifies gravity and quantum mechanics, but also unveils the mysteries that dance throughout the cosmos. Yet, as enticing as it may sound, this theory introduces a captivating twist that defies simplicity while paradoxically making profound sense. It necessitates 10 dimensions of space-time, far beyond the 3 dimensions of our tangible reality. Conceptual models designed by physicists offer glimpses into these unfathomable extra dimensions. Imagine a 2-dimensional pond, home to fish oblivious to the concept of height, restricted to perceiving length and width. The notion of a 3-dimensional existence eludes them entirely. However, when raindrops bless the pond's surface, creating ripples, the fish bear witness to the effects of a dimension beyond their grasp, a dimension they cannot directly experience. Likewise, physicists surmise that we too are blind to the extra dimensions of space-time, unable to observe them directly, yet we discern their influence on the familiar world we inhabit. The string's vibrations within superstring theory propagate waves of energy through these enigmatic dimensions. These waves manifest as particles endowed with distinctive attributes like mass and charge. Hence, superstring theory presents a potential explanation for the particles and forces that shape our universe, encompassing even gravity's enigmatic hold. Nevertheless, there exists a perplexing conundrum. The dimensions demanded by superstring theory are minuscule, eluding direct scrutiny. Our laboratories can only probe the 4 dimensions we perceive: length, width, depth, and time. How then can we ascertain the existence of these concealed dimensions? Perhaps the extra dimensions are cunningly curled, concealed from our sight. Picture a sheet of paper meticulously rolled into a compact cylinder. Were you an ant tracing its surface, the curvature would remain undetected. Analogously, the extra dimensions in superstring theory may coil into infinitesimal loops or spirals, evading our gaze while subtly shaping the vibrations of the strings within them. Another scenario suggests that during the Big Bang, the extra dimensions may have been more apparent and observable. According to certain versions of superstring theory, the universe originated in a state of 10-dimensional space-time, with all dimensions equally visible. As the universe expanded and cooled, the extra dimensions gradually contracted and curled up, leaving us with the 4 dimensions we currently perceive. If this hypothesis holds true, there may be remnants or clues of the extra dimensions present in our surroundings. The mathematics involved in superstring theory are incredibly intricate, unearthing uncharted territories in the realm of mathematics. However, unraveling the puzzle of a quantum black hole has proven to be an elusive challenge. Despite numerous attempts by physicists, no one has yet achieved a breakthrough. Edward Witten of the Institute of Advanced Study at Princeton has referred to superstring theory as 21st century physics that fell accidentally into the 20th century. Recently, several groups of physicists independently announced a significant advancement. They discovered that string theory could provide a complete resolution to the quantum black hole problem, albeit in only 2 dimensions instead of 10. Many physicists believe it's merely a matter of time before someone cracks this enigma, given that the equations involved are well defined, albeit difficult to solve. For now, it remains premature to purchase tickets for intergalactic voyages or time-traveling escapades, particularly concerning black holes. With all of these complexities, one thing is evident: a multitude of questions exists alongside a myriad of potential solutions. Michio Kaku elucidates how determining the true answer amidst these bewildering theories is no simple task. He emphasizes that the issue of infinite answers is not exclusive to string theory. Numerous prominent theories possess an infinite number of solutions. Newton's laws, for instance, can predict the motion of diverse objects ranging from rocks to rocket ships, but specifying the desired explanation is necessary before predicting their movements. These specifications are known as initial conditions. Similarly, in string theory, one must delineate what the theory describes. Unlike other theories, however, the initial conditions in string theory correspond to the Big Bang itself, necessitating the specification of unknown conditions at the moment of its inception. Several approaches can be taken to address this predicament. One possibility is to experimentally ascertain the initial conditions at the instant of the Big Bang and allow string theory to elucidate the subsequent evolution of the universe. Currently, there are already string theory solutions that depict the progression of our universe since the Big Bang, based on reasonable estimates of its nature. Another more ambitious approach is to require string theory to determine its own initial conditions. However, this is a more intricate and less probable proposition. Consequently, we have already significantly narrowed down the possibilities. Nevertheless, Michio Kaku and string theory present an alternative perspective. Perhaps the Big Bang was not as monumental as commonly believed. Kaku suggests that it was not a colossal explosion devoid of the thunderous noise one would anticipate from a bang. The Big Bang theory fails to elucidate the cause or mechanics behind the purported explosion. It simply affirms its occurrence. The truth is, we need a theory capable of accounting for events preceding the Big Bang. This is where string theory comes into play. According to string theory, our universe might have materialized through the collision of distinct universes or emerged from another universe. The interconnection between these universes takes the form of a wormhole, resembling a conduit joining 2 bubbles. It is plausible that we have already detected evidence of this umbilical cord linking our universe to another. In a peculiar manner, we could be dwelling within a black hole all this time, oblivious to our true state. Do you believe there is validity to this theory? Share your thoughts in the comments section below.